Hey y'all, welcome to the lesson for 8.3. Can be found on these pages here in your geometry books. We're talking about today similar polygons and scale factors. That is a lot of what we will hit in this lesson, along with a couple other things here and there. And so let's check out a definition first. Let's get right into it. When two polygons, and a polygon, remember, is just, in kind of a loose definition, is that it's a shape. It's all connected at the endpoints. There's no overlapping. There's no extension of the endpoints over where they're supposed to intersect, and it's totally encompassed. There's no open parts left. So when two polygons, they could be three-sided, four-sided, and so on, triangles, quadrilaterals, etc. When two polygons have congruent corresponding angles, and proportional corresponding sides, and let's underline those words there. Congruent angles, proportional sides. The sides won't necessarily be the same length, but they may be in proportion to one another. So they may be in the same ratio from one side or from one polygon to the next polygon. We're going to check that out. That's why we've been learning about ratios and proportions all along here, so we can finally talk about how they're related to geometry more in similar polygons. So proportional corresponding sides, they are called similar polygons. That is what we're defining here. So they're called similar polygons. They look the same, they just are kind of different sizes. They could even be the same size. Then we'll learn about what that's called. That's a special case. But I'm going to put example 1, I think, on the next page. Yes. So example 1, decide whether these figures, what figures, Mr. Wagner? Patience, young one. So whether these figures are similar. So what figures, you may ask, am I talking about? It's these figures that I'm about to draw. So let's say that we have one shape that looks like this. Just some general quadrilateral. I'm not saying it's a kite. It almost looks like a kite, but we're not going to assume that's the case. And then nice thing about this, I'm going to copy and paste this. I'm going to duplicate it actually, and I'm going to move it over here. I'm going to resize it, and so based on that, I am actually keeping the shape the same, but I'm just kind of making it smaller. I could actually make it bigger. So this way, this is a nice tool that this program has that I'm using. It is going to be similar, but we're not going to assume we can trust the looks. We're going to assume that even though they look like they're similar, it looks like that one is just a bigger, blown up version of another, that we have to trust what's in the picture, trust the markings and the numbers given in the picture. And so yes, they look similar, but just like with congruent figures, just because they look congruent, just because they look similar, doesn't mean we can assume that they are. And so we're going to say that this is T, H, E, and Y. We always blame a lot of things on they, like they said this or they did that, and so they apparently know. Yes, don't we do that? We do that a lot. Who's they? Who is they? You're just passing the blame on to somebody else. So we're going to say that T matches up with K, one mark, that H matches up with N, 2 and 2, E matches up 3 and 3 with O, and that Y matches up 1, 2, 3, 4 is going to match up with W over here. 1, 2, 3, 4. So the first part holds where we have congruent corresponding angles. So that's good. That's one of two things we need to check to see if they're similar. So that's good. But let's see now about the sides. So this is going to be 36. This will be 48. This one's going to be 40. And this one 32. over here in this one, this is going to be 36 here, 30, 24, and 27 up here. And let's solve our problem here. So the solution, we've already said it, corresponding angles are congruent. So let's just write that down. All, we can shorthand corresponding like that, just write C-O-R-R. All corresponding angles are congruent. So that's part 1 of 2, but we also need to check, are they proportional? So let's ask that question here. But are corresponding sides proportional? So is that true? Let's find out. How can we find out? We check the fractions and check the matching parts. So it looks like they, T-H-E-Y, is going to match up in the same order as K, N, O, and W, as no. And so 48, compare that to 36. We're comparing TH compared to KN. What is that fraction equal to? 48 over 36. If you reduce that, you can divide by 12, would go into both of those. That's the biggest number that I see. That would be 4 over 3. This is a pretty important number, so let's circle that. Not a final answer, but pretty important, so we'll circle it here. So now I need to compare the rest of them. I need to compare TY to KW. That's another valid, it should be a valid way to check. If this is the same, reduced 36 over 27, if this is the same as this was over here, then this side compared to this side is going to be proportional to this side compared to this side. So that proportion, we're comparing fractions. Does this equal 4 over 3? Divide by 9. Divide by 9. Yep, it does. So we're good to go so far. We've checked 2 of the 4 sides here. If we had a pentagon, we would have to check 5 fractions. If we had a heptagon, we'd have to check 7. A dodecagon, we'd have to check 12, but we only have 4 here, quadrilateral, so we just need to check 4 different fractions. So let's see, HE compared to NO. If you look at that, 40 over 30, hopefully that's pretty clear. You can divide each one by 10 and get 4 over 3 as well. We're 3 for 4. We're almost there. Let's check now EY compared to OW. Is this going to work? Is this going to finish it up? Will it culminate in a proportional way? Are these going to be similar? Divide by 8 and you have a yes to that question. 4 over 3 is the same thing there. So corresponding sides, yes they are. They are proportional since corresponding sides are proportional. We already said the corresponding angles were congruent. So are proportional. Yes, we can say that the figures are similar here. So put the letters, just like congruent figures, the letters have to go in the corresponding order. Same thing with similar figures. They have to go in corresponding order. So T-H-E-Y matches up in the way that K, N, O, and W matches up. So this, but we can't put, we're not going to write are similar to every time. We have a symbol for this one as well. Congruent was like that. It was equal to with a tilde. This one, we take away the equal sign. We just put the tilde. So we just put that mark there. It doesn't have to be that big, but it's just a little squiggly line, one single squiggly line. They is similar to no. At this point, get out your different color. Pause the video if you need to do that. But I want you to write down what that says or how you would read that. So if you're reading this out loud, you'd say is similar to. So they is similar to no. And that'll do it for example 1. So let's define another thing. Define scale factor. We defined similar polygons already. What is a scale factor? If 2 polygons are similar, so we just saw that meant corresponding angles are congruent, corresponding sides are proportional. If they are similar, the ratio of the lengths of corresponding sides. And notice I'm abbreviating corresponding most of the time in this lesson here, like that, of corresponding sides, is called the scale factor. It's called the scale factor. So if we go back to this example, the scale factor here would be 4 to 3. 4 over 3, or 4, and then you can do the colon and a 3 like we saw in a couple lessons ago, I think that was. So the scale factor, write this down for me too, the scale factor of they to know in example 1 was 4 over 3, or you can write that as 4 colon 3. Scale factors, generally you're going to see it more often like this. Maybe I shouldn't say that quite, but quite often you'll see it like this, and sometimes you'll also see it like this. So either way is acceptable. You have to know both ways. Right? So that is what scale factor is, and then a theorem. Theorem 8.1. First theorem, wow, that's a long ways to go for a first theorem in a chapter for geometry, but 8.1, first theorem in this chapter. If two polygons are similar, the ratio of their corresponding sides equals the ratio of their perimeters. And so I'm not going to do an example of this one in the context of the notes here, but I will point out how this works. So if we went back to example 1 and we added up all these, so 48 plus 36 plus 32 plus 40, why don't I get out the calculator to show you that this works. So 48 plus 36 plus 32 plus 40. Okay, let's keep this number in mind. 156. So 156. Let's see what the perimeter is of this other one. No. We had 156. This one, 36 plus 27 plus 24 plus 30. Okay, 117. So 156 divided by 117. That should be the ratio of their perimeters. And you get 1.33333. This is the same thing. 0.3 repeating is 1/3. So this is 1 and 1/3. Or in other words, 4/3. So we just demonstrated that the ratio of the perimeters is going to be equal to the ratio of each individual side comparison. And so that's all that theorem says. Sometimes that can be helpful in solving the problem. So let's check out a final example though. Example 2. Okay, so this is a pretty famous picture. Whoops, there's my page browser. Go away. Pretty famous picture from, I believe that was World War II, where a lot of the young men of our country were off fighting in the war, and the women had to take over a lot of the jobs, and there was this sense of patriotism and pride in what the women were doing, helping to keep the country going in the absence of all those young men. And so we're going to just kind of for fun and kind of a little interesting history side note to insert that into here. So in the picture, because life's more than just math, right? What? Did you just say that, Mr. White? Yeah, definitely. Life is more than math. Okay, so other subjects are also important. If I have not emphasized that in class, triangle. There we go. She is similar to can. Okay, so we can do it. She can do it. Triangle. She is similar to triangle. Can. Find the value of x. And so we need to draw a picture down here. Let's put some triangles down here. So could they be the same size if they're similar? Yes. Usually one's going to be bigger than the other though. I want you to make this one look like a right triangle, but we're not going to put in the box in the corner, so we're not going to assume that. And then don't draw the next one yet. You can draw this one in position there. Looks like I didn't draw a perfect right angle, but again, we're not assuming that it is. But I will duplicate this and move that over here. This one I'm going to rotate around a bit, and then I'm going to shrink it down a little bit too. Actually, I meant to flip that over, so I'm going to rotate it around back to there. I do want to shrink it down. I think I've got this fancy tool here. Let's see if I can find that. I'm going to pause and see if I can find that. Okay, there it is. Transform, and I want to flip in the y-axis. Okay, so all I did was take that shape and adjust it so that it was still proportional this way to this way, and then I shrunk it down, or I did shrunk it down, and then I flipped it over the axis. But if I were to undo all that, if I were to unflip it and then blow it back up again, I would be good. But I don't want to do that. I want to keep it like that. So we're saying that these things are similar, and the way I did that, it guaranteed that the actual looks of it would match up too. So I want you to try to draw similar triangles as best you can, and she is going to be similar to can. So these things need to match up. The S is matching up with the C part over here, the A with the H, and the N with the E. And so if I reflip that over and made it a little bigger again, that would match up. C would be right on top of the S, A with the H, and N with the E. And let's give some labels to these. We're going to say this is 6 and this is 8. And then AN we're going to call X, and CA or AC we're going to call that one 3. So since these are similar, this is what we can do with a problem like this. Since they're similar, we can set up a proportion and solve it for X. So if things are similar, we can compare similar parts to each other. And so we're going to have, well, SH. These two letters are the first two letters here. They should match up with the first two letters over here. SH should match up with CA. So I'm going to make that comparison, and I'm going to compare that to HE compared to AN. Notice those are the second pair of letters. In a sense, the second and third letters here should match up with the second and third letters here. So this would be HE over AN. SH, that is 6. CA is, that is 3. And over here, HE is 8. AN we're calling X. So we did this a little earlier where we saw that we can cross multiply here. We could also think of it as 6 over 3 is the same as 8 over what number? Hopefully you know this is 2, and so this would be 8 over 4 is 2. So X would equal 4. Let's say you didn't see that though. Different color, let's put the cross multiplication in there, and then let's do that, the numbers there. So let's just assume you didn't see it. Later on, if you do see those shortcuts, you can take those shortcuts there. Just be careful so you don't take too many shortcuts or you don't do the shortcut wrong. You would say X equals 4 on this one. And that is going to be it for this one. Just going to do those two examples. We'll go over some more together in class. Hopefully you found that helpful as you tackle 8.3.